In this video, we are going to discuss the electric field. So the electric force on a charge is exerted by the electric field created by other charged bodies. So we're going to continue our analogy with the gravitational force equation that we learned in Physics 151. In Physics 151, you would have learned to calculate the gravitational field strength, or the symbol lowercase g, and that was equal to a constant times the mass of the object exerting the force. So, for example, we could say the Earth, and then divided by the distance between the Earth and some point of interest, so divided by r squared. So we're going to see a similar analogy here, where a charge exerts an electric force by another charge coming into its electric field. That electric field is present regardless of whether the charge experiencing the force exists or not. This is why when we calculated lowercase g, the mass of, say, the moon was not included, because if we want to know the gravitational field strength from the Earth at the moon's distance, it's not created by the moon. That strength is just dependent upon the distance from the Earth. So we're going to see something very similar here, where the electric field from a charge exists whether or not a test charge is present somewhere in the field. It just happens to be at a test charge when it's placed, experiences a certain electric force due to the electric field, due to the size of the charge creating the field and the distance from that field. So once again, we're going to see a distance dependence. So we can calculate the electric field strength due to a point charge by using Coulomb's constant, so the 9 times 10 to the 9 newtons meters squared per Coulomb squared, times the charge exerting the electric field, or creating the electric field, generating the electric field. So this is the charge that is creating the electric field, not the one experiencing the electric field, the one creating it, divided by the distance squared. So you would be determining the distance from the charge creating the field to some point of interest. So rather than even putting a charge there, I could just ask you what the electric field of point A, some distance away from the charge is. Electric field strength does not get its own unit. So your unit is going to be newtons per coulomb. When we're talking about point charges, or essentially any type of charge, we're going to get to things more complicated than just a point charge in the next topic. Electric field lines are going to point away from positive charges and towards negative charges. And this matters because electric field is a vector. So this means when you're finding the electric field strength due to multiple charges on a particular point, so if I put a Q here and say this charge is negative, and say this charge is positive, since it's a positive charge, this one is going to point away from the charge, so this would end up being in the positive x direction, and the Q is negative, so this one is going to point towards the charge, so this would end up in the negative y direction. This means if I was trying to actually calculate this, I would end up with a x component and a y component, so I'd have to use Pythagoras theorem and inverse tangent to find magnitude and direction in this case. Now I do want to reiterate here that this equation is solely for a point charge. We're going to learn in topic 22 what to do when the charged item is not a point charge. So we're going to do distributions of charges, but we'll get into that in topic 22. But keep this in mind. There's a reason why the equation sheet is labeled just for a point charge. We can also talk here about the equivalent of Newton's second law. So we learned force equals mass times acceleration back in Physics 151. We have a similar relationship, it turns out, for electric forces, where the electric field strength is equal to the electric force divided by the charge. We do have to be careful though, because this Q here is the one experiencing the force. So this Q here is going to be essentially what we refer to often as a test charge, the charge that we stick into the field to test the electric field strength, and that then leads to it experiencing a specific electric force based upon its own charge and the electric field that it's in. So this one here is the test charge. So the one experiencing the force. This Q over here is the one exerting the force. And these have to be two different Q values. So you're not going to have a charge exerting an electric force on itself. It's going to be one charge that creates an electric field, and that electric field in turn exerts an electric force on whatever charge is within that particular field. And that electric field strength is going to vary based upon the distance that the test charge is from the charge exerting or creating or generating the electric field. So this is very similar to the idea of you can be in the Earth's gravitational field, but you aren't necessarily going to experience the same gravitational force. This is going to depend upon your own mass, and it's going to depend upon your distance from the center of the Earth. So you experience less gravitational force once you get to the outer regions of the atmosphere compared to the surface of the Earth. And you also experience a different gravitational force compared to your neighbor, because that's why when you step on a scale you see a different value. Because you have a different mass, you're going to have a different gravitational force exerted on you by the Earth's surface, even if you're standing at the same distance from the Earth. So you're going to see the same thing with electric charge, where the electric field depends upon the charge exerting or creating that electric field, and then whatever test charge you happen to put in it leads to a different electric force. The electric field strength does not have to be constant. So it could be uniform or it could vary from point to point. So with the point charges, since there is a distance dependence, you're going to find that the field is not uniform. So the further away from you get from the charge that is exerting the force or creating the electric field, you're going to see that the electric field strength decreases. So it's not uniform. There's a distance dependence. We're going to talk in topic 22 about some charge distributions that do lead to a uniform field. So no matter the distance from the distribution of charge, the field strength is going to be the same. The other thing I want to point out here is the idea of electrostatics. Electrostatics is going to occur when the field strength is zero. So this is very similar to what we would have seen when we were summing forces in Physics 151, where you added a certain number of forces together, and when you sum them, it got zero, so the acceleration was zero. Very similar here, where you might have a charge on one side of the point and a charge on another side of the point, and when you sum the electric forces or electric field at a particular point in between them, you find that the electric field is zero. So if you put a test charge at that particular point, you would find that the charge doesn't move because there's no net force to actually push it around. So you can see something very similar to where we had mechanical equilibrium before. Now we're going to have electrostatics, where the electric field strength is zero, so there's no electric force exerted, so a charge wouldn't move when put at that position. And that's going to be very important in the beginning portions of this course. We're going to create situations where the electric field strength is zero.